Okay, enantiomers. And I'm pretty sure we're all sick of hearing the word, so I'm just gonna go over this one. Hopefully not that fast or slow. Anyways, all right. Enantiomers. Enantiomers. Real simple. They are stereoisomers that are chiral. And I swear to God, you guys better remember what chiral means. Mirror images that cannot match up. No matter how much you rotate them, no flipping around, no matter how much you rotate them, they don't match up. Right? Chiral Stereoisomers. Okay. And enantiomers usually contain one or more stereogenic centers. These are also called chiral centers, and we're going to go over what they mean in a little bit. So put in the back of your head, or maybe in the side of your notes. Okay. And an enantiomer, something very important, is that they always have two forms. So if it's an enantiomer, you will have two different conformations, not configurations. Enantiomers don't have configurations. They don't have that E and Z stuff. They have conformations. So they're going to have R and S stuff, okay? Enantiomers deal with rotations. And they have conformations. Not configurations. Enantiomers, conformations. Maybe they might have configurations, but for the sake of this video, let's just say they really just have conformations. Because I didn't go through enough examples or notes to, make sure that that's certain. Anyways, there are different types of enantiomer or chiral compounds. So imagine you have this like really big candy bag. Not some candy bag. Inside of it, you've got this new type of candy that's really cool. It's really great. I don't know what flavor it has. It's called an enantiomer. So cool, such a great candy. It hasn't even been invented yet. So who knows? Now, when the enantiomer candy bag, well, you can have a mix. You can have a mix of enantiomer flavors, I guess. There are two flavors of enantiomers that exist. You have the blue flavor, have the red flavor. Okay? And these two flavors have names. You have the S flavor that comes in red, it stands for strawberry, and the blue flavor that's in blue that stands for blueberry. Let's go with raspberry. Raspberries are red. Blue raspberry. Okay. Just to recap, we defined our enantiomers here: chiral stereoisomers, stereogenic chiral centers, and they have conformations, not configurations. Now, I'm talking about this new candy called enantiomer that comes in two flavors: blueberry and strawberry. So blue raspberry, that's what blueberry is. It's really cool. It tastes great. Okay. And in this bag of enantiomers, you can have a mix. You can have a mix of them. So you can either buy the racemic mix, not racist, racemic, where you have 50% come in blue raspberry and the other 50% come in strawberry. 50-50. It's a 50-50 mix. If you really hate one of the flavors, you can have the Chiral mix. Right, let's make this one a bit smaller. Chiral, which is really, you just pick one of the Enantiomer flavors. I like blue raspberry better, so I'm going to go with this one. So, racemic mix, you get a 50-50 mix of enantiomers, right? Chiral mix, you get a pure 100% only one flavor, because for some reason you're an asshole and hate the other one. And the final type of mix you can have is the scalemic mix. Very fancy. And it's basically just any non-50-50, non-pure mix of enantiomers. So you can have a 30-70, 40-60, 55-45, 13.5, 100 minus 13.5, so on and so forth. So it's basically just an uneven mix of the two. So recap. 3 different types of mixes of enantiomers they can have, or we can call this as different types of chiral compounds. Okay, so we've got a racemic mix, 50-50, scalemic, any non-50-50, and homochiral, which is just one flavor, just one enantiomer, one type of enantiomer. And this racemic, scalemic, homochiral mix, they're just different ways for you to describe a chiral compound. What is a chiral compound? An enantiomer, literally. Personally, I have no actual idea towards when you would say racemic mix. Maybe it's like in a solution. They have different enantiomers of the same molecule. Or in a candy bag. I don't know. I don't think it's like one molecule though that has like, no. Yeah. So we'll probably see these mixtures and like solutions and stuff. So maybe your solution says, oh, it is pure and we only have the R flavor of enantiomer. Then it is pure. Or maybe you get one that says you have 50% S, 50% R flavor, and it's a racemic mix. So on and so forth. Hopefully that makes sense. Now let's move on. All right. Chiral centers or stereogenic centers, up to you. Call it what you want. Let's get another color. Stereogenic or chiral centers. Now, there are a few rules to what a chiral center is. I can just go ahead and tell you, a chiral center is a tetrahedral center with 4 different substituents attached. So, really easy. Tetrahedral. Hopefully we remember that from a few, like 2 videos back, I think. Tetrahedral. Now I've got 4 different substituents attached to it, or the way I want to see it, 4 different colors, because that's easier. I think that's easier for everyone than saying 4 different chemical whatevers. All right, 4 different colors. And this little center right here, so atom right here, guess what? It's tetrahedral, attached to 4 different colors, sorry, substituents. Yay, it's a chiral center. Congrats, that's all there is to it. No, it's not a chiral center. Take this. Guess what? You replace this red one with another green one. This here is not a chiral center. No, it's an abomination. It's an imposter. Do you know why? Because it's not attached to 4 different substituents. It didn't include the red one. It's not attached. See, it's green here. And if you're not attached to 4 different substituents, you're not a chiral center. So if you want to be a chiral center, be inclusive. Have 4 different people hold your limbs in a tetrahedral shape. Don't just go for the green. Go for the red. But don't just go for the red. Go for the orange and the pink and the green too. Be a chiral center. Inclusive. Anyways, chiral center is tetrahedral, 4 different substitutes, 4 different colors attached. All right. And a really cool fact is that if your chiral center, this dude here in the middle, is not a carbon, it's not configurationally stable. And that's just fancy for it's not stable. It will change shape really, really easy. Like it'll just like, I don't know, molecules will just like rotate around it like that. They'll go like that. And it's just a mess. So if you're not a carbon chiral center, you are not configurationally stable, you are pretty much a mess. More on that, maybe never. I don't know. All right, and there are different types of chiral centers, of course. So this right here, it's called point chirality. So let's go ahead and define all of this. Point chirality. Point chirality just means that you have a chiral atom, an atom, and it's attached to 4 different stuff. 1, 2, 3, 4. We're just going to draw them as an X, check, circle, and square. Point chirality. That's it. The atom is chiral. It's tetrahedral and is attached to 4 different substituents, 4 different stuff. Now we've got another type, which is axial. Basically, we've got an axis. Okay, we've got an axis. And this axis is actually a bond. It connects 2 atoms. And each of these atoms are connected to 2 other things. In this case, I think it's okay if they're not all different stuff, but an example I have is not showing all different things. So square, this one triangle. Here, this axis here is a chiral axis. Chiral. All right. So, interesting thing about this chiral axis is that each of these little atoms here, they are sp2 hybridized. So what do I mean? Well, they're attached to 1, 2, 3 points, 3 things. sp2, sp2. You see, these sp2s, they're kind of like facing each other. You know, they're both looking this way, and what that creates is a 90-degree, kind of like a twist. 90. Already, because of the degree symbol. 90-degree twist. What on earth does that mean? Well, put simply, it just means you got your first one here, right? And you got an X here. You got your double bond, your other atom. sp2, they're facing each other, right? Gonna create a lot of tension right there if they're just like directly like this, right? It's like if you have like two really big guys are just like standing in front of each other and there's this like small doorway, and they're trying to like get through, that door, but they're hella big, like they're massive. It's gonna create a lot of tension between them. Not the sexual kind, hopefully. So what are they going to do? Well, like any normal person, they're going to twist and go past each other. And that's what these molecules literally do. They don't face this way. No. They create a 90-degree twist. See how it just twisted that way by 90 degrees. Now they're like this. There's no more big tension between them. They can pass by each other. Everything is okay. Peace is restored. And because of this twist right here, the molecules, they end up being chiral, and that's what creates a chiral axis. What do I mean? Well, let's go ahead and draw. Let's draw mirror of symmetry. Got our we can make a new molecule X, and maybe another X here, and a square. It's just going to be drawn like this for now. I will make it in 3D later. All right. And now we're going to have our twist, which I'm going to draw here. All right. That might make it a bit easier for you guys to visualize it. All right. So because of this 90-degree shift right here, these atoms, they can't be put on top of one another anymore. So you see, no matter how much I rotate them, they're not going to be on top of each other. Like, yeah, this one's now up and this one's sideways, but guess what? This is an X when it should be a square. They are now chiral. Flip them, they're not going to be the same. And this is what makes the molecules chiral. So this 90-degree twist that happens here, right, to kind of relieve some of that tension in a way, as well as the fact that you have a different different stuff here and here and here and here and so on and so forth. It makes it so that you have axial chirality. Very cool. Now, really quick, before we do any CIP and RNS stuff, we're just gonna go over final type of final thing is planar. This thing, chirality. Oh yeah, we said it. Planar chirality. And this is just enantiomers that have a chiral plane instead of a chiral axis or a single atom that is chiral. So we have a circle here, which is our plane, and another one here. And maybe we'll have an atom right here connecting over here. And then we'll have another atom here, which is a square, and one more, which is an X. All right. And then guess what? We're going to reflect it. Wow. Now what happened? Well, first of all, we have a chiral plane. So that's going to be this whole thing right here. This is our chiral plane. This stuff right here, all right? Let's just call that our chiral plane. Or maybe it's more like this. I guess it's more like this, yeah. It's more like that. Either way, it's there, it exists. And guess what? Because we put this, because we put these substituents here, our molecule has become chiral. We can no longer become one another. It is impossible, it is not meant to be. However, if we remove them, wow, oh, not that too. Just want to remove the substituents. Damn it. Okay. If we remove them, guess what? I'll remove this too. We can become one another. Yay, we can. We are literally one another. We are the same. We match up. Destiny works. But we have the substituents. The fates have been sealed, collided, and broken. We can no longer match up. Because that is chiral. They are chiral. All right. Now to something that's a bit maybe backtracking. So we covered the 3 types of chirality that we're going to see. And yes, there's octahedral chirality, but if you're a nerd, go up and look that up in your own time. Because I mean, I'm not going to go for that. Of course, you can always like send me like a text or something. I don't know if I put my phone number on the site. Maybe I did. And be like, oh, you asshole, you skipped octahedral chirality. And I'll just block you. Anyways, let's see. All right, CIP. So, remember when I said that enantiomers? Damn it. They come in 2 flavors called R and S. Well, that's a real thing. It's not a real candy, but it's a real thing. There are always 2 types of conformations for an enantiomer. There's the R conformation or the S conformation. Now, what the fuck is that? Well, it comes from this thing called CIP, which is where we're going to start. So a long time ago, some dudes went like, wow, enantiomers look really similar. Like, how can I tell if this guy right here, same as this guy, or that he's different from this guy? Like, bro, look, they're so similar. How can I tell? And this dude, he went like, you know what? Why don't we just call them R and S? And that's how we're going to tell. And all the science dudes are like, wow, you're so smart. That's so cool. And that's exactly what they did. That's literally what they did. For us to be able to tell the difference between 2 enantiomers, we labeled them as R or S using CIP rules. Why do we use CIP rules? Because they are literally the guys who created R and S. Okay? So let's take a look at what these actually mean, R and S, and how to determine them. And let's start with something really easy, like colors. Let me just check that these are mirror images of each other. So I've got some colors here. I've got my chiral center, got my enantiomers, mirror images. No, they will never match up. Unfortunate, they will never match up. Now, I'm going to start labeling them with numbers 1 through 4. Why 1 through 4? Because there are 4 things attached, literally. And to go ahead and label these colors, I'm just going to go with the classic rainbow order. Blue, green, orange, red, as we all know. So blue comes first, then comes green, then comes orange, and finally we have red. Same thing, we're going to go over here. Blue, green, orange, and red. Great, now what? Well, now we are going to go ahead and kind of orient this molecule so that this part here, the part that is facing away from us, is facing away from us. Let me show you what I mean. We're going to draw something called the Newman projection. And the way that we do this is that first we draw a circle. Then we draw, I like drawing them like this. Some people might draw it with this thing looking like this, but I like it. I do it like that. It doesn't really matter though. Now we're going to do some thinking. All right, we've got this molecule here. And the way I drew it so that this part is facing away from us. Notice how this Newman projection only has three little sticks. That's because when we draw it, we don't care about the guy that's facing away from us. He's facing away from us. Fuck him. Yeah. Fuck him. None of us like him. He doesn't even want to be here, so we don't draw him. Okay, we just don't. He's supposed to be here. Technically, he can be over here. That's the way they draw it, right? So it kind of looks more 3D. But he's not here. At least in this Newman projection, when you do CIP, he's not one of us. He does not exist. So let's go ahead and label this the way we should, without the guy in the back. So we've got orange on top, green to the side, and red. And the same thing over here. Just gonna go ahead and copy, paste. Same thing here. This blue guy, he's facing away from us. He's not one of us. He's not a part of the group. He's facing away. So we're going to draw it kind of looking this way. Okay. Red. Green. Orange. All right. So now remember how we numbered them earlier? We're going to go ahead and put those numbers in here. Green was 2, red was 4, orange was 3. Green 2, orange 3, and red was 4. Cool. Let's go ahead and move these up. All right. So now what? We've got our two mirror images. We've got our Newman projections. Now what? Where's the R? Where's the S? Well, in order to do that, we gotta see the order that these atoms are in. So watch this. We're gonna play a really cool game we probably did as a kid called Connect the Dots. But this time we're really connecting numbers. Watch. 1, 2, 3. We are spinning this way. One more time. 2. Oh, no, don't do that. 2, 3, 4. Connect the order of the numbers in numerical order. No, not 3, 2, 4, not 4, 3, 2, not 2, 4, 3, not any other combination you can think of. It is literally the lowest number to the highest one in numerical order, okay? Come on. If you need help, use your fingers. 1, 3, 4. And as you can see, as we connect them, I'm spinning to the right. It is an R conformation. Connect the dots and you spin to the right, you have an R conformation. All right? R does not stand for right. But in this case, why not? It probably should. I'm doing the same thing over here. Connect the numbers, 2, 3, 4. Spin the pencil. Spin, 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 spin. Wow, we're going to the left. No way, this confirmation is L. No, it's not. It's actually S. This is the S confirmation, where we spin to the left. In R, we spin to the right. In S, we spin to the left. R to the right, clockwise. I don't know what other way you can call it. S to the left, anti-clockwise, counterclockwise, and I don't know how else you can call it. That's how you determine R or S, okay? And that's pretty much RNS, CIP, but now I gotta do it for chemistry and not colors. But it's the same idea, except instead of ordering things by the classic rainbow order, you're ordering things by their atomic mass. But this can get kind of tricky real fast. So let's go ahead and think up of an example. Let's say that we've got our carbon center here. Attached to it, 1, 2. Fun fact, when you have like colored in wedges like this, it means that it's facing towards you. When you have these dashed guys, it means that they're facing away. It's carbon, it's attached to an oxygen, another carbon, hydrogen, and the nitrogen. Actually, I don't even know the molar mass of nitrogen. And a chlorine. Let me look up its molar mass. Yep, and the chlorine. Going to go ahead and draw our little mirror. Make it a bit smaller to make some space. Copy, paste. Turn them like this. They are now mirror images of each other. I hope you guys can read backwards. No, I'm kidding. I'll just fix them. There you go. It's just a little carbon though. Okay. All right. Let's start numbering what we've got. We can do this in red. Okay. So the lightest atom we have here is a hydrogen. This is a 4, and that is a 4. The heaviest one we have is a chlorine. 1, 1. So I guess you can think of this as pretty much fat shaming the molecules or atoms. But I probably shouldn't say that. It's kind of rude, yeah. Don't do that. You're weighing them by their worth, not their mass. Okay. Anyways, oxygen 16, right? And carbon, I think, should be 12. Probably should know this. Right. Got our order. Time to make our Newman projection. Okay, draw our circle. And who's facing away from us this time? Who's the bitch that we don't like him or her or them? Well, it's chlorine. See, it's got this little dashed shape right here. That means it's facing away. Okay, so let's think about what does the molecule look like when chlorine's in the back. Well, looks like that we're going to kind of look at it from here. This one, we look at it from here. All right, try to like kind of rotate it. H, go down. Okay, that means oxygen's here. Go to the left of H, we've got carbon. Copy, paste. Here we've got H and O. If we go kind of to the left, I guess, and to the right, we've got a carbon. All right, put back in our numbers, and we've got the hydrogen at 4, 3, 2. Hydrogen at 4, 3, 2. 2, 3, 4. Spinning to the right. This one is R. 2, 3, 4. Spinning to the left. This one is S. Now, what happens if we're attached to multiple multiple atoms that just kind of happen to be the same, but they're full, I guess. Bits are different. So what I mean by this is instead of having an oxygen here, we've got another carbon, and it's double bonded to an oxygen. All right. So when that happens, we gotta bring up something called ghost atoms. So basically what's going on is that we're gonna number a ring. All right, number a ring. Hydrogen 4, it's the last one. Chlorine, it's 1, 1, first one. Now we've got 2 carbons. So what do we do? Well, we write out everything that that carbon is attached to. And we use this thing called the something something of outward exploration. I know it sounds all manifest destiny and cool and whatever, but it's really not. It's more of a headache. So let's just get on with it. Okay, so this carbon right here, what is it attached to? Well, it's attached to 3 hydrogens. I'm gonna put in hydrogen, hydrogen, hydrogen. This one is attached to an oxygen. Oh, but wait, it's got a double bond. There's a double bond. We add in 2. That's a trick. And I think it might also be attached to hydrogen. So oxygen, oxygen, hydrogen, double bond, so I get 2 oxygens. This one here is just 3 hydrogens. Now we just look at these two and ask ourselves, okay, so which one is attached to the heaviest atom? Yeah, it's this one. Okay, oxygen is insanely heavy. It's this one. It's not heavier like that heavy. It's just like 2 more than carbon, but it's heavier than the hydrogen. This one loses. This one wins. So this means that now we have this one at the number 2 and this one at number 3. 2, 3. All right. Yeah, you can make your Newman projection and go ahead and number them. Interesting fact, however, let's say something like, oh, what if we had, let me just take these out. Oh, if we had this carbon here, it's also attached to an oxygen. Okay. And the hydrogen, and the hydrogen. And this one attached to a sulfur. Well, guess what? Same idea. Instead of stopping at this carbon, you just go on to the next one and look at the oxygen. What else is the oxygen attached to? Well, it's attached to a lone pair, maybe, probably. Sulfur weighs more than a lone pair. So this would still be the 3rd one. Remember that you are looking for the heaviest atom, okay? Which one of these has the heaviest atom attached to it? This one here has a sulfur. It doesn't matter if this one has 2 oxygens. This one has a sulfur. It's way heavier than an oxygen. This one wins. This one's going to be second, okay? So it doesn't matter if like, oh, the 2 oxygens crossed out or whatever it is. Second one of them has the heavier atom. It wins hands down. All right. All right, so I just checked the notes and stuff, and that should be about it for the basic enantiomers, CIP, and RNS. As always, if you guys have questions, feel free to contact me. There is a form on the website that you can fill out if you have a question about something. I will happily make a video on it. And yeah, as always, check out the website. Subscribe if this channel is helpful to you. And yeah, I will see you guys next video. Okay, awkward goodbyes. Where's it stop?